There are a variety of ways to communicate and represent compounds in chemistry. One way we communicate information about chemicals is writing their chemical formulas, which consist of the chemical symbols we see on the periodic table, as well as subscripts or coefficients when necessary. These formulas can either be categorized as a molecular formula or an empirical formula. A molecular formula is the formula that represents the actual molecule at hand, while an empirical formula is the simplest version of the chemical formula at hand. For example, if we discuss a chemical you may be quite familiar with, caffeine, we would say its molecular formula is C8H10N4O2. As you can see here, in the structure of this chemical there are 8 carbon atoms, 10 hydrogen atoms, 4 nitrogen atoms, and 2 oxygen atoms. You may have noticed that we have an opportunity to simplify all these numbers while maintaining the same ratio among them. We can do this by dividing each number, or subscript, by 2. This is how we get the empirical formula, which for caffeine is C4H5N2O. The subscripts are not the same values, but they do have the same ratios. It is important to note that not all molecular and empirical formulas are different. For example, the ionic compound that is table salt can only be written as NaCl, which is already in its simplest form. NaCl is both the molecular and empirical formula for sodium chloride. The same goes for water, or H2O. H2O is both the molecular and empirical formula for water since it represents the actual number of each element in the molecule while also being in its simplest form. We can use these formulas to help us calculate the elemental composition of molecules. Elemental composition is typically expressed by percent by mass, also known as percentage composition. We can calculate this using the mole ratio. Before we hop into an example, how is the mole ratio going to help us? Well, when you see the subscripts of a molecule, those numbers give you information on the mole ratios regarding the elemental composition. Let's take a look at the water molecule as an example. For every 1 mole of water, we will need 1 mole of oxygen and 2 moles of hydrogen. So we can use these values and relate them to the molar masses we see on the periodic table to help us calculate percent by mass. Let's try finding the percentage composition of magnesium bromide. The molecular and empirical formula for magnesium bromide is MgBr2. We want to know what percent by mass magnesium takes up in this compound as well as the percent by mass that bromine takes up in this compound. We know that for every 1 mole of MgBr2, we need 1 mole of magnesium and 2 moles of bromine. Let's calculate how much this is in terms of mass. We will multiply 1 mole of Mg by the molar mass of Mg, which is 24.305 grams per mole. The moles cancel out, leaving us with 24.305 grams of magnesium. Starting with 2 moles of bromine, we will multiply this by the molar mass of bromine, which is 79.904 grams per mole. This equates to 159.808 grams of bromine. Now that we have the masses calculated, we need to turn these values into a percentage. Whenever you need to find the percentage of something, you take the part, divide it by the whole, and multiply by 100. In this case, our whole value will be the total mass of MgBr2, 24.305 grams of magnesium, plus 159.808 grams of bromine equals about 184.113 grams. So, the percentage composition of magnesium in MgBr2 is equal to 24.305 grams divided by 184.113 grams, multiplied by 100 equals 13.2%. Now we could either do some easy subtraction to find the percentage composition of bromine since we know these two values will add up to 100, but let's keep practicing and we can still use this idea to check our work. The percentage composition of bromine is equal to 159.808 grams divided by 184.113 grams, multiplied by 100 equals 86.8%. 86.8 plus 13.2 adds up to 100. So we know our calculations are looking good. It also makes a lot of sense that bromine takes up such a large percentage by mass of this compound since we not only require double the amount of moles for this chemical, but it also has a significantly larger molar mass than magnesium. We can also use this process backwards, meaning we can use percentage composition to determine the empirical formula. This is actually the very common order of operations for scientists, since they collect samples, can determine the elemental composition of the sample via instrumental analysis, and from those values must determine the empirical formula. Let's give this a try. Say you find a sample of iron oxide, and after analysis in the lab, determine that it is 69.94% iron. Based on this information, what is the formula for this iron oxide? Our job is to determine the values of X and Y in this generic iron oxide formula, FeXOY. First, we can determine the percentage composition of oxygen with this given information. 100 minus 69.94 is equal to 30.06. So this sample is 30.06% oxygen. To work with these values easily, we will let the total mass of our iron oxide be equal to 100 grams, so that the mass of iron is equal to 69.94 grams and the mass of oxygen is equal to 30.06 grams. From the mass values, we will calculate the mole values of iron and oxygen, which will become the subscripts X and Y in FeXOY. We can do this by dividing the mass of the element by its molar mass. Here we will take 69.94 grams of iron divided by 55.845 grams per mole, which is equal to about 1.25 moles of iron. Then we will take 30.06 grams of oxygen divided by 16 grams per mole, which equals about 1.88 moles of oxygen. Our ratio of iron to oxygen is 1.25 to 1.88. These are not the pretty whole numbers that we like to use for subscripts in an empirical formula. The first step in getting them to whole numbers is dividing all values in the ratio by the smallest value, which in this case is the 1.25. After dividing 1.25 and 1.88 by 1.25, the ratio is now 1 to 1.5. Our next step is to multiply all the values in the ratio by some number that gets the values to be whole numbers, which in this case we can do by multiplying by 2. After multiplying the 1 and 1.5 by 2, our ratio of iron to oxygen is 2 to 3. This means our empirical formula is Fe2O3. You may come across some examples where the value you must multiply your ratio by in order to achieve a whole number ratio is not as apparent. So it is normal to go through a trial and error process to determine this. Let's take this example one step further and determine the molecular formula of this compound. This can be accomplished when given the molar mass of the compound, which in reality would be experimentally determined. Let's say we determine the molar mass of this iron oxide to be 319.38 grams per mole. Let's compare this molar mass of the unknown molecular formula to the molar mass of the known empirical formula. The molar mass of the empirical formula can be calculated as follows: 2 times 55.845 plus 3 times 16, which equals 159.69 grams per mole. To find out how much bigger the subscripts need to be, we will calculate how much bigger the molar mass of the molecular formula is compared to that of the empirical formula, like this. 319.38 divided by 159.69 equals 2. This means the molecular formula is double the empirical formula, so we can multiply the subscripts of the empirical formula by 2 to get the molecular formula, which in this case would be Fe4O6. Now that we have talked about how moles apply to solids in chemistry, let's take a look at how we can use it with solutions. Solutions are homogeneous mixtures that consist of at least two components, including a solvent and a solute. Solutes, which are the components of solutions that are dissolved into the solvent, are the major part of a solution that determines the solution's general properties. For example, salt water is a solution consisting of a solvent, water, and a solute, salt. While the solvent is usually the major component to a solution, water is always considered the solvent of a mixture even if it is a smaller component of the solution. This is because water is a universal solvent. It can dissolve more substances than any other liquid due to its chemical and physical properties. Qualitatively, we organize solutions based on the mass or mole ratio between the solute and the solvent. Larger amounts of solute dissolved in the solvent create concentrated solutions, while smaller amounts of solute dissolved in solvent create dilute solutions. The rule of thumb used for this differentiation is that a solution is concentrated if there is significantly more than 10 grams of solute per 100 grams of solvent, while a solution is dilute if there is significantly less than 10 grams of solute per 100 grams of solvent. Quantitatively, we organize solutions based on their molar concentration, also known as molarity. This is represented by a lowercase c. Molarity is the ratio of amount of solute to volume of solvent, as seen in this equation. Molarity is typically expressed in moles per decimeter cubed, which can also be written as moles per liter, but the IB exam specifically wants you to use the decimeter cubed version. For very dilute solutions, units of millimole or micromoles may be preferred. Let's take a look at an example. If we dissolve 2.45 grams of copper 2 chloride in 50.0 centimeter cubed of water, what will the molar concentration of CuCl2 in this solution be? To answer this question, we need to use our molarity equation, which is moles of solute over decimeter cubed of solution. We are given grams and centimeters cubed, so we need to do some converting before we can divide. We turn 2.45 grams of copper 2 chloride into moles by dividing by the molar mass of copper 2 chloride, which is 134.45 grams per mole. This gets us 0.018 moles of copper 2 chloride. Now we convert centimeters cubed to decimeters cubed, and our conversion factor is 1 decimeters cubed is equal to 1,000 cubic centimeters. We take 50 and divide it by 1,000 to get 0.05 decimeters cubed of water. We now plug both of these into our molarity equation, 0.018 moles over 0.05 decimeters cubed, and we get a molarity of 0.36. We represent this molar concentration unit with a capital M, so we would write this answer as 0.36 molar solution of CuCl2. This equation can of course be manipulated in multiple ways if you are asked to calculate a different variable, which could be either moles of solute or volume of the solution. A chemical formula written in square brackets is the correct notation to express molarity of a substance. So for this last example, we would write our answer as open bracket CuCl2 close bracket equals 0.36 molar. Looking back at the molarity equation, we find the molarity by dividing moles over volume. But sometimes chemists want to compare the mass instead of the moles, in which we can use a very similar equation. We simply remove the moles in the numerator and use the mass instead, which is represented in grams. We call this equation the mass concentration, which is represented by a lowercase p. Now, all of these concepts are relevant because chemicals within solutions are usually concentrated when stored, and it is common practice to dilute them down to a less concentrated state when they are being used in the lab. The concentrated solutions are called stock solutions, and you will likely encounter them while you are working through your chemistry course. These stock solutions contain a known concentration of the solvent, and with that information, these equations can be used to create a solution with a desired, more dilute concentration. Let's take a look at how this can work. Suppose you created a standard solution of calcium chloride, CaCl2, by dissolving 13.64 grams of calcium chloride into 250 cubic centimeters volumetric flask. You then use this stock solution to create a diluted solution in which you take 5 cubic centimeters of the stock solution and transfer it into a 100 cubic centimeter flask and fill the remainder of the flask with deionized water up to the 100 cubic centimeter mark. What would the concentration of calcium chloride be within the new solution? To solve this, we can use two different versions of this equation. We start by finding the concentration of the standard solution. We find the molar mass of the compound by adding together one calcium atom at 40.078 grams and two chlorine atoms at 2 times 35.45 grams. This gives us a total molecular mass of 110.98 grams per mole. We then divide 13.64 grams of our given quantity by the molar mass. So we know that the solution contains 0.122 moles of CaCl2. We divide 0.122 moles of CaCl2 by the volume of the stock solution, which is 250 cubic centimeters. But we need to use decimeters here, and 250 cubic centimeters is equal to 0.250 cubic decimeters. So 0.122 moles divided by 0.250 gets us a molar concentration of 0.488 moles per cubic decimeter. This again is for our standard stock solution, which we can use to calculate the concentration of the new solution. We took a 5 cubic centimeter sample of the original solution, which we can convert to 0.005 cubic decimeters. We calculate the moles within this sample by taking the molar concentration of 0.488 moles per cubic decimeter and multiplying it by the volume, which is 0.005 cubic decimeters. This gives us 0.0024 moles of CaCl2 in this small sample. When we dilute this sample with deionized water, the moles of solute does not change. So we can keep this value constant and use it to find the molar concentration of the new solution with the new volume. So we take our molar concentration equation and solve for C for the new solution. We take the moles of CaCl2, which is 0.0024, and divide by the new volume, which is 100 cubic centimeters, making it 0.1 cubic decimeters, and get a molar concentration of 0.024 moles per cubic decimeter for the new solution. Now let's take a look at how we use moles to measure and quantify gases. Avogadro was not only known for his value of 6.02 times 10 to the 23rd particles per mole, but also his law. Avogadro's law states that at standard temperature and pressure, if two gases take up the same amount of volume, they will also contain the same amount of particles. First of all, what is standard temperature and pressure? Standard temperature is 0 degrees Celsius and standard pressure is 1 atmosphere. These standard values are important because the further the temperature and pressure deviate from these values, the more particles will not behave ideally. So this relationship between amount and volume can be represented by this equation here. N1 over N2 is equal to V1 over V2, where N represents moles and V represents volume. And the subscript 1 reflects information regarding one gas, and the subscript 2 reflects information regarding the second gas in the problem. Let's try an example together where we are given information about a reactant and need to calculate information about the products in a gaseous reaction. The balanced chemical equation representing the synthesis of oxygen and hydrogen gas to produce water vapor. If a volume of 0.85 cubic decimeters of hydrogen gas is used, what will be the volume of oxygen consumed and the volume of water vapor produced? According to our balanced equation, the stoichiometric ratio of hydrogen to oxygen is 2:1. So the volume of oxygen consumed in this reaction will be half the volume of hydrogen consumed. This can be seen when plugging the known values into our equation, substituting 2 for N1, 1 for N2, and 0.85 cubic decimeters for V1. To solve for the unknown volume, we will end up dividing 0.85 by 2 after some algebraic manipulation, as seen here. So the volume of oxygen consumed will be equal to 0.452 cubic decimeters. The volume of water vapor produced can be solved in the same fashion, except this time the stoichiometric ratio between hydrogen and water vapor is 2:2. Which means the starting amount and volume of hydrogen is equivalent to the amount and volume of water vapor produced. So, the volume of water vapor produced from this synthesis reaction is 0.85 cubic decimeters. In a case like this, it is relatively simple to calculate the information desired without the equation that can be used for Avogadro's law. But it is there for you if you need to double check your work or encounter values that you feel more comfortable plugging into an equation.